Okay, so let's talk about power, torque, and speed. And so, but first let's review a little bit. I'm going to review energy. We talked about energy before. Energy is the capacity to change the environment. Okay, so if you have energy, you can make things happen. So in a practical sense, when our battery is fully charged on the robot, that robot can do things. It can make change. You know, it can shoot a ball, it can drive, it can change its position, it can launch itself at high speed over the ramp and get some air. It can beat the poofs, yes. We'll see. But then we talked about this thing called work. And work is the transfer of energy by the application of a force. And actually, I could put in parentheses here, or a torque. Torques can do work too. Although when you think about it, a torque is a force times a lever arm distance, a twisting force. And so when a motor applies a torque to a gear system, whatever, it is transferring energy, electrical energy that's flowing through the motor gets transferred to the machine by the application of a force, and this force applies a torque and makes things spin. Now, to also review, we said that work was equal to a force times a displacement. And so this was equal to, units-wise, this was a Newton times a meter, and we defined a Newton times a meter to be a joule, or capital J. So it's just to review some of the stuff we did quite a while ago, though. Okay, well, now we're gonna talk about power. And did we briefly talk about power before?
I believe so.
I think we did a little bit. And we said that power was the rate at which energy is transferred. And now if the energy is being transferred by the application of a force or a torque, we can say that the energy that's being transferred is work, and we can say that power, we use the capital letter P for power, is equal to work over time. And what units did these have?
I remember what it is.
Don't you remember what it is?
Watt.
Yeah, it's an old joke. Joules per second, that's a watt. Abbreviated with a capital W. Now, it's unfortunate that the unit for power is the same as the variable for work, but such is life, people. Get over it. You'll only see, if W follows a number, like you're measuring something and it says like 20 W's, that means 20 watts. If you see, W equals F times delta X, well, that W now is representing a quantity of work. So this represents a unit, this represents a quantity. But they both start with W, so there you go. Well, here's something that we talked about. If we say work is a force times an application, or times the displacement, and then we divide that by time. Well, what is delta x over delta t? What is my, how far I go divided by the time it took me to go that far?
Velocity.
That's called velocity. And so, and this was in the notes, you know, on that VEX, those VEX notes I had you take, but they said power is equal to force times velocity. And if you want to get watts, this has to be in newtons and this has to be in meters per second. Okay, in order to get watts. A newton times a meter is a joule, divided by a second is a watt. So if I give you something in pounds and feet per second or something like that, well, you would have power in foot-pounds per second. I guess that could be a unit for power. But you would have to convert all that. If you want it into watts, you'd have to use unit conversions to get it to watts. But what about torque? And this will be new. I think we did this before. But what about the power due to a torque? Well, let's think about a wheel that we're going to apply a torque to. And the wheel can be a gear or a pulley or, you know, sprocket. I'm just going to draw it as a circle. And I'm going to apply a force to it. So here's the force, and here's my wheel. And so I think you can see that a torque is being applied here because here's your R. And remember, we said torque is equal to R times F. This is the lever arm distance. For what we do in here, we'll just call that the lever arm distance. I don't think I'm going to give you torques where the R and F aren't at 90 degrees to each other, because that's pretty much all we do, right? I can't think of an application that we would use where that's not true.
Pretty much anything rotating at all just
Yeah.
90.
There might be if we ever have to build an arm, which there's no arm in this year's game, but if we ever have to build an arm, then we might have to worry about torques where the R and F are not at 90 degrees to each other. Because really, technically, and this is for you AP physics people or people close to it, torque is R cross F. And the definition of a cross product is you take the first vector, multiply it by the second vector, the magnitudes of them, multiply by the sine of the angle between those two vectors, and then the direction you get with the right-hand rule. Now that's far beyond the scope of this class. I'm just saying it to be complete. But you will next year. Okay, but this is what we're going to use. The radius of the wheel times the force. But imagine I have a wheel like this and I'm applying a torque to it. Is any energy being exchanged if it's just sitting there? No. In order for work to be done, this force has to be applied through a distance, through delta x, we said. Although delta x here is kind of weird because this thing's spinning. So here's what I'm going to do, and I wish I could draw in animation, but if you can imagine this force staying perpendicular to the circle. Okay, everybody watch this. And we're going to pull this circle around. Okay? Watch. Stop texting. Look up here. The force is right here. And you pull with that force, and you keep that force, tangential to the circle, and I'm going to pull it around. Then I'm doing work. Because I'm going, yeah, and I'm transferring energy from this guy into this device. And maybe this is transferring energy by turning a wheel and making your robot move or something like that, or making a wheel spin. So let's do that. Let's go through here. And so now the force is going to be like this. And notice that R, here's R times F, and R is still perpendicular to F. So perpendicular means sine of 90 degrees is 1, so we don't have to worry about any of that stuff. But look at this. This is kind of like my delta x. Now this is going to get a little mathy, so hang on. I know, some of you, it's like addition I've seen is hard, but I think you can do it. All right, so pay attention. Now, this right here is an arc length. Instead of delta x, I'm going to say that the work done by this force is force times delta s. Okay, does that make sense, everybody? Delta s. If I were to take a string and wrap it around that sector of the circle, hey, it's really the arc length. It's the length of this of distance from here around here. That's delta s. Okay. Well, but it also rotated an angle. This is my delta theta. Okay. Now, we talked about radians a few weeks ago. We have to go back to that. And so what I'm going to do is I'm going to say that this delta s right here, so the work that got transferred by applying that force and making this thing rotate is the force. Now, delta s is equal to r times delta theta. Oops, that's right. Remember, we defined the radian. We defined delta theta, an angle, as being the section of the circle, delta s, divided by the radius. And we said, okay, well, that's an angle. Well, what I'm going to do is solve this. This is just solved for delta s. Delta s, this distance, is equal to this angle in radians times the radius. So, I'm going to substitute. I'm going to say this is F times R delta theta. So delta S is R delta theta. So the work done now can be written this way, and this is going to really, this is going to make sense. Okay? So hang on and think. We have F, this force applied through this displacement, doing work, transferring energy into this system. But what is F times R? It's the same as R times F. That's the torque. So F times R is torque. Torque times delta theta is work done. Okay? Now, remember when we defined torque, and we got like, this was newtons, and this was meters. And, you know, force is measured in newtons, and R is measured in meters. So how come a torque isn't a unit of energy? No, it's not. Because here's kind of what you have to do. You have to think of this as Newton meters per radian. But we haven't multiplied by a radian yet. So look, if I've got my pencil right here, and I'm going to apply a torque to it and try to make it and try to do work on it, if I do this, okay, massive amounts of force I'm applying to this pencil. But I'm not doing any work until on the pencil until I rotate it through an angle. It's just like a force. If I apply a force to the pencil, okay, the pencil's not moving, so I'm not doing any work on it. But when I apply a force through a displacement, okay, now I'm doing work on the pencil. I'm transferring energy from, into this system. So now this is now how we calculate work from a torque. It's when you have a torque, but that torque has to be applied through, you have to twist it through an angle, and listen to me, the angle can't be in degrees, and it can't be in revolutions. It must be in radians in order to calculate work in joules. Yes? Yeah. Yeah. Now, we just said that power is work over time. So let's say power equals work over time. Work over time. Well, now the work is the torque I apply times the angle through which I twist that torque divided by time. Well, what is this? The rate at which I change my angle. That's angular speed. And what variable did we use for angular speed? Not W, no. Omega, thank you. You'll never get into a fraternity or a sorority if you call it W.
In all rotational stuff, it's W and fish.
No fish. All right. Torque times omega. Now, if you want this in watts, if you want to get it to watts, this will be in, this torque will be in Newton time meters. Sorry. And now it's really newtons times meters per radian. And of course, this has to be in radians per second. So when you multiply them, you get Newton meters per second, which is a joule per second, which is a watt. So the power put out by a motor is equal to the torque the motor is applying to your system times the rate at which it's spinning in radians per second. And this is a very useful thing to know when you're trying to design a robot. And it's got different DC motors, and they apply torque, and you want to know how much power it's going to take, because as we're going to get to later on, power and voltage and current are all related. Yes? So this is the basic equation that I wanted to get to today. I mean, we can say power equals force times velocity if we're dealing with the linear system. But it equals to torque times angular velocity if you're dealing with a rotating system. And by the way, this is a very common thing you'll see an analog between linear systems and rotational systems. Here, a force is applied to an object that's going at a certain velocity, or a torque moving at a certain angular velocity. So force and torque are analogous. Velocity and angular velocity are analogous. So let's back out and take a look at the whole thing. And using these ideas, later on we'll work some problems with motors and power and torque and speed. And then we'll include that with gearboxes and all that. That is all.